Oh, can everyone see my screen? Okay, we're going to start in about like 1 minute, just to let people come in. Wait, can you hear me now?
Yes.
We're just giving
Yeah,
everybody like a
Rishabh,
minute
can you
to
hear me?
join.
Oh, Rishabh, can you hear me now?
Yes.
If not, oh, okay, good. So we're gonna go ahead and start with our lesson. We're gonna finish last week's lessons on diagonals and polygons, and then we're gonna go on to circles. So, oh, we started on this last time, and I think you guys should have a general idea of this already. So I'm gonna go over the solution right away. So if you remember, let's see, if you remember from last lesson of how we learned how to count diagonals, an important tool we learned was to look at each vertex, right? So let's see. So if I have like some polygon, right? And so let's say I have an n-gon, right? So if I look at one vertex, I can't go to obviously itself, and you can't go to the next adjacent vertices, because otherwise that diagonal would really just be a side. So for each of the n sides, I can go to n minus 3 diagonals. But you have to be careful here because you overcount by 2. So like if I have like, for example, a hexagon, pretend this is a hexagon. Again, these are the vertices. I'm overcounting this one, this line segment from here and from here. So you overcount everything twice. Therefore, you need to divide n times n minus 3 by 2, and that will give you the amount of diagonals in an n-gon. And using this idea of looking at one vertex is going to be very helpful in the next example. So go ahead and try this if you haven't already. Oh yeah, and for those of you who don't know, a polyhedron is just a 3D shape. It's like a cube. Like imagine a cube. A cube is a polyhedron. A tetrahedron is a polyhedron. So you don't really need to know like 3D geometry to solve this. And yeah, go ahead and try this problem.
just imagine basically piecing together one square, one hexagon, one octagon, all the way around.
Sahil, you're muted.
Yeah, he's just giving you guys a bit of time to try to solve the problem.
Right.
If you guys are stuck and just like how to approach this problem at all, I think a good way would be to first find the amount of vertices in this polyhedron. Like that seems like a good idea because I don't think you can get very far without knowing that. So first, try to find the amount of vertices in the polyhedron. Then second of all, you're asked for the amount of things that lie inside of the diagonals that lie inside of the polyhedron. So what I would recommend you to do is to just draw a vertex and to see what diagonals you cannot go to. Okay, so those are my two tips. So there's no like formula here. It's just like you need to learn how to focus on one vertex. So basically, find the amount of vertices and then focus on one vertex, and look at the diagonals that are invalid. That should give you a hint to which ones are valid. Go ahead and try that. So I'm going to go ahead and scroll down. I won't just go through the solution, but I will let you guys see the diagram of how a vertex looks. So maybe this will help you. Okay, so I'm gonna go ahead and um walk you guys through what basically how to solve this problem. So going back to the problem statement, given that we have a polyhedron and it has 12 12 faces, 12 squares, 8 hexagons, and 6 octagons, all of which are regular. And we were also told that at each vertex of the polygon, of the polyhedron, 1 square, 1 hexagon, and 1 octagon. So, as I said before, I think a good starting point would be to look at the amount of vertices in total. So, if we just draw it out, remember that we were told that 1 hexagon, a square, and an octagon meet at a vertex. So, if you just like look at this vertex, you can see that it's like corresponds to a vertex of the square. So, like basically, how you can think of this is that every vertex can be linked to exactly one corner of a square. So, like if you look likewise at this corner, let me just so if I have like one corner here, one vertex here, there's also going to be like basically the same picture but on this side of the vertex. Like, all of these vertices will look exactly like the blue vertex and this whole picture. So basically every single vertice corresponds to one corner of a square. So that means since there are 12 squares and there are 4 corners to a square, there are 48 total corners in total corners of squares in total, which gives you the amount of vertices. So now we know that there are 48. Actually, let me scroll up. We know that there are 48 vertices in total, right? So now we want to find the amount of diagonals that lie inside the polyhedron. But a good way to do this is to just find the amount of diagonals you can draw in total, subtract the ones that are invalid. That's just going to give you the valid vertices. Valid diagonal. So catching the ones that are invalid, we see that we can go to this one, or we can't go to the orange ones because those are the ones that are directly adjacent to it, and that will create a diagonal that just gives you a side. And obviously, you can't go to the same one, same vertex again. And remember, you can't lie on a face, so it can't lie here, can't lie here, because all these lie on a face. So if you just count all these up, there's what, 5 here, so there's 5 invalid ones, like 5 red lines, and then there's 3 red lines here. So 3 red lines, 1. That gives you 9 red lines. And you also can go to the orange vertices or the blue vertices. So all the x's one, if you basically just count them up, you're just going to get 9 plus the amount of invalid ones, orange, 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 plus blue, 4, which means you can go to 13 diagonals. 13 vertices from a given vertex. So since we know that we have 48 vertices and we can't go to 13 of them, that means we can go to 35 of them, and those will lie inside the polyhedron. So we know that if we just multiply 35 and 48, we will get something that is double our answer. And the reason why, it's the same problem, same idea as above. You're double counting at each end of a diagonal. So like, if you connect this one to another diagonal that's inside the vertex, you're going to count it twice because you count it once from each edge, each vertex. So you have to divide this by 2. So just to summarize, what this means is that you can go to 35 vertices from each of the 48 vertices, but you're overcounting by 2. So really our answer is just 35 times 24. So this is 100. So if you multiply this out, this will give you 840. And that's our answer. And this might seem like a different element, different subject than geometry, and I think it sort of is. It's actually like sort of combinatorics like, and if you guys don't know what combinatorics is, it's basically just a branch of math where you don't really need any advanced math concepts, but you just need to be able to think in really clever ways. So here you can see we didn't necessarily use any formula, but we did have to like carefully think our way through this problem. And this was from an AMY test, so it's already pretty hard. And on top of that is a question number 10. So don't feel like bad if you guys can follow this problem. When you guys study combinatorics, this will make a lot more sense to you, but hopefully it already made some sense to you. So I'm going to pass it over to Caleb while we'll go over Polygon Area. So Caleb, do you want to take the screen?
Sure. 1 second.
Caleb, are you there?
Yep. I'm trying to pull up the PDF. Alright. Did that work?
How do you find the area of the hexagon again? I forgot.
Alright, can you guys see my screen?
Yep.
Alright. So we're gonna move on to Polygon Area. And this is also still continuing from last week, but it's still a pretty important topic. So we've already done triangle areas and quadrilateral areas, so we can actually put them together to get the area of polygons. So one of these examples is going to be, so our first example is to find the area of a regular hexagon if we're given that the side length is 8. So see if you guys can solve it. I'll probably give about a minute here.
What's the area of the hexagon again?
Alright, I'm going to move on to the solution. So first of all, we haven't covered how to find the area of a whole hexagon. So we can actually just break it down into pieces, like here. So if we connect the opposite vertices, we end up here is 6 equilateral triangles. And this is because each interior angle for a regular hexagon is going to be 120 degrees. So this right here is 120 degrees. So if we split in half like this, each one of these is going to be 60 degrees. And if we have that, all of them are equilateral. So each of these 6 little triangles in total is going to form up the area of the entire hexagon. And we're given that the side is going to be 8. So we know this is 8. So the area of each of these little equilateral triangles is side length squared root 3 over 4. So it's just going to be 16 root 3. And because we have 6 of those, if we multiply this by 6, we're going to get our answer as 96 square root of 3. And yeah, as you're able to see here, we can find the area by just simply breaking it down and cutting it apart. So next problem we have is finding the area of a regular octagon. This time it has side length 4. So I want to see if you guys can figure out some clever ways to find the area. If you do have any ideas, post in chat. Yeah, I encourage you guys to try drawing it and see what you can do. Alright, so now I'm going to move on to the solution. So if we draw this octagon here, what we end up getting is this square-looking shape if we extend the sides, like Sahil said. We know that the interior angles are 135, and we're able to find out that extending the sides gives us a square because we can break that down into 45 and 90. So since this right here is 135, since this is 180, this side right here is going to have to be 45. And if that's 45 and this side's 45, this has to be 90. And given that on all four sides, if we have this 90-degree angle on all four sides, what we have here is a square. And we know how to deal with squares. All we have to do is find the area of this big square and then just subtract the smaller triangles in the corners. So we can go ahead and do that. Oops, let me scroll down. So we're given that each of the side lengths is 4. So we can find the area of these little triangles. Since AH is 4, I'll mark it up here. Or since each of these sides are 4, we can find that the legs of these smaller triangles are going to be 4 over square root of 2, which is 2 root 2. And if we have that, each of the little triangles is just going to be the leg squared divided by 2, and that's going to be 4. And we know that the square wxyz is just going to be one of the sides squared. So in this case, that'd be, let me clear this first. So we're going to have wh plus hg plus gz. So each of these segments here. We already know hg because we're given that's 4. And we know that each of these smaller segments are 2 root 2. So in total, the area of the square is going to be 4 plus 4 root 2 squared. That's going to be 48 plus 32 root 2. And then all we need to do is subtract the area of the 4 triangles we had before. And that's going to give us our final answer, which is 32 plus 32 root 2. As you can see here, again, we used a simple shape to find the area. But instead of cutting it apart, all we had to do is take the area as like the leftover parts after cutting things off. So depending on what your problem is, try thinking both ways, because one of them might work. So now let's move on to finding a general area, a general formula for a regular polygon. So given like the center of a regular polygon, basically the point equidistance from all the sides and vertices of the polygon, that's the center. And if we're given that the distance from the center to its sides is k, and then the length of each of the sides is s, find a formula for the area of an n-gon in terms of kn and s. So I'm going to give you guys probably 2 or 3 minutes to try to solve this one. I advise you guys to try connecting the center point to the vertices. Again, drawing it out is quite helpful. All right, I'm gonna move on to the solution now. Wait 1 second. Shoot, wrong button. Okay, so if O is the center of the polygon, what we can do is we can cut the polygon into n triangles. So if we try connecting the center of each vertex we basically end up with a bunch of triangles. So let me draw you an example right here. So if we draw this polygon here, and here's the center, where we connect the center to each of the vertexes, we end up with that many triangles, and the altitude of each of the triangles, basically from the center to the side, we're given as k, and the base of each of the triangles we're given as s. So together we can find the area of each of the triangles, and we know there's going to be n triangles because there are n sides. So if we simply multiply the area of one of these small triangles by the total number of triangles, we get the area of the entire thing. I'm gonna go ahead and mute everybody because I think someone is repeating the audio. All right. It is so basically we know that the area of the small triangles is going to be k times s over 2, and there's n of them. So for any polygon, regular polygon, the area is going to be nks over 2. And do note that this only works for regular polygons. If we have a really odd shaped polygon, it's not going to work because each of the triangles isn't going to have the same area. And something you might want to know is the distance from the center to each of the sides is sometimes called the apothem. So if you ever see that word, you know what it means. We can also see from here that the perimeter of the polygon is going to be n times s. So our area formula can also just be half the perimeter times the distance from the center. And you can see where that comes from. Let me clear this. We're going to be moving on to circles. So we're done with polygons for now. Here are some definitions. The circumference is basically the perimeter of a circle. So this curved line is a circle. Pretty sure all of you are familiar with this term. This right here, this is called an arc. So it's like a partial circumference. And it's measured in degrees. So imagine if the center of our circle is right over here. This degree right here, whatever angle this is, we call that arc that many degrees. And from there, basically, we can know how long that arc is based on the angle it covers. So the entire circumference would be 360 degree. It would be a 360 degree arc because it covers the entire circle. However, while all 60-degree angles are the same, all 60-degree arcs aren't. And that's because the radius of a circle will differ. So if you have a really small circle, a 60-degree arc on that circle is going to be tiny. While if you have a really big circle, that 60-degree arc is going to be a lot longer. So in order to in order to be able to find the measure of an arc, you not only need to know the angle, but also the radius of the circle. So here's a little fun thing if you want to try to calculate pi by yourself. If you measure the circumference of a circle and then try to measure the diameter, and you put the circumference over the diameter, you're going to get pi. And depending on how carefully you took that measurement, you're going to be closer to this number. This constant is called pi. I'm pretty sure you've all seen the symbol before. And pi is pretty unique because it's irrational. So it never repeats. You can't express it as a ratio of integers. And it never ends, basically. It's an infinite series of non-repeating numbers. One thing to note is that because of this, we found the circumference of a diameter is equal to pi. We can replace that diameter with 2 radius as well to find that the circumference is 2 times pi times the radius. Here's 100 digits of pi. So if you do want to memorize that, you can. There are plenty of competitions out there solely based on memorizing this infinite number. All right, so the first problem we're going to have is finding the circumference of a circle. Finding the radius of a circle given the circumference as 32 pi. So I can draw this for you. This is our circle. We're given that the outside is 32 pi. And go ahead and find the radius and type it to nearest a hill. Alright, I'm going to give you guys about another 30 seconds or so. Remember our formula for the circumference before? Go ahead and apply that. Alright, so let C be the circumference and D be the diameter. We already know that C divided by D is pi, and we're given that C is 32 pi. So D has to be 32. That's pretty simple algebra. And we know that the radius is half the diameter, so 32 divided by 2 is 16. It's a fairly simple problem, so I hope you all got that. Next, we're going to start dealing with arcs. So we're given that the length of a 72-degree arc is 15. So try to find the circumference of the entire circle. And I can give you guys a little bit of a diagram here. So given that this arc right here has a length of 15, and this is 72 degrees, find the radius, find r. Sorry, I didn't mean the radius. I meant the entire circumference. My bad. It'd be this. All right. So we're given that this 15-degree arc is this arc that has length 15 is 72 degrees. So that means that 15 units is 72 out of 360, which is 1/5 of a whole circle. So in order to find the circumference of the entire circle, all we need to do is multiply that arc length by 5. So basically, a 360-degree arc for that circle would have a length of 75, and 360-degree arc is the circumference. Next, we can introduce chords, and a chord is just a line between 2 points on the circle. So given that a chord YZ on a circle has length 12, and the circumference of the circle is 24 pi, you're asked to find the length of arc YZ. So the straight path has length 12. Find the length of the curved area, the curved path. All right, because of time, I'm just going to go ahead and move to the solution. In order to find the length of the arc, we need the angle, YOZ. First of all, let me just draw a quick diagram. We're given that the circumference is 24 pi. Let's say we have y here and z over here. We're given that that length is 12, and we're trying to find this arc length. And the middle is O. We can first start by trying to figure out lengths. We know that since the circumference is 24 pi, diameter is going to be 24 and radius is 12. So that's from OY and OZ are each going to be 12. So that triangle right there in the middle is equilateral. And because of that, angle YOZ is going to be 60 degrees. And to find arc YZ, that's going to just be 60 degrees over 360, or 1/6 of a circle. So 1/6 of the circumference would be 4 pi. So that's how we get our answer, 4 pi. And the central angle is the angle with the center of the circle as a vertex. So that'd be angle YOZ right here that we found was 60. And we've figured out now how to relate arcs to a central angle. So this is a pretty useful thing to know. We clear that. And given that chords AB and CD of a circle have the same length, try to prove that their corresponding arcs are going to be equal in length. So given a circle here and 2 chords, so here and here, prove that if these 2 are equal, these arcs right here must be equal as well. Alright, so we can start this problem by just connecting lines, because we don't have that much information right now. So if we draw each of these points to the center of the circle, we end up with some triangles, and that we can work with. We know that these are radii of the circle, so each of these lines connecting to the center are going to be equal. And we also know that AB is equal to CD. So by SSS congruence, these two triangles are going to be congruent. And because of that, these angles right here, they have to be congruent as well, because the two triangles are congruent. And because of that, the arcs are going to have to be congruent as well, because the arcs are based on the center angle. So using that, we're able to show that if the two chords are equal, their arcs are going to be equal as well. And basically, here's our theorem stated out. If the two chords are congruent, the arcs they subtend or cut off are also going to be congruent. And it works the other way around too. So if the arcs are congruent, the chords are going to be congruent as well. This is probably going to be the last problem we're going to be able to do, because we have about 2 or 3 minutes left of the meeting. So let's take a look at this problem.
Are we gonna rejoin?
Probably not. Most people.
What? Where is the diagram? Where is the diagram?
Oh shoot, we forgot to put in a diagram. Here, I'll draw it for you. So basically, what we have here is a path right here. So a semicircle. We have point A here. Point A at this corner, point B at this side, and point C at the top up here.
Okay.
And the question is asking how much longer must she walk if she walks along the edge of the circle instead of taking the straight path from A to C and C to B. So yeah, if you have any ideas on how to solve the problem, or if you are able to solve the problem, post in chat. All right, given that this right here is 180.
So where is the says that there is a center O, but I can't see that in the diagram you show.
Well, the center is just going to be over here.
Oh, and we're gonna cut off in about like 2 to 3 minutes. So Caleb, while you're explaining, and the participants in this call, just be wary of that.
Yeah, if you do get cut off, you know what happened. Anyways, we can go on to solving it now. So, well, first of all, you might see that since this is a semicircle, this triangle right here is going to be a 45, 45, 90 degree triangle. But if you don't, what we can do is we can first connect point C right down to the center of the circle. And what we have there is since we have that these two arcs right here, these two arcs are going to be equal. So we know that the angle are going to be equal as well. So since we have angle AOC is equal to COB, which is equal to 90. OA, OB, and OC are all radii of the circle. So these two triangles right here, let me change colors. This triangle are going to be congruent. And we're given that AB is 180. So AO, OB, and OC are all going to be 90 yards because they're all radii of the circle. And AC and BC, the straight paths, are going to be CO root 2, which is 90 root 2 yards. And because AB is half of a circle, its length is going to be AB times pi divided by 2, which is 90 pi yards. So Anna must walk 90 pi minus AC plus BC, which if we substitute in, is going to be 90 pi minus 180 root 2 yards. That's square root. 180 root 2 yards farther if she follows the curved path. Well, I hope you guys learned something from this. We are going to be emailing out the recording